Now, we will talk about the power series.
A power series is one that takes the form c sub n times x to the nth power from n is equal to 0 to infinity. So, we get c sub 0 first with no x because x to be 0 is 1. Then the next term is c sub 1 times x, then c sub 2 times x squared, then c sub 3 times x cubed, and so forth. These c's are constants that we usually call as coefficients. And the sum of these series can be represented as function f of x. F of x is equal to c sub 0 plus c sub 1 times x plus c sub 2 times x squared plus c sub 3 times x cubed, and so forth, where we just add up all the terms resulting in what looks like a polynomial with infinitely many terms. The domain of this function is the set of all x values for which this series converges. Also, we can see a power series in this form. C sub n times the quantity of x minus a to the power of n from n is equal to 0 to infinity. And the sum of this series can be represented as f of x is equal to c sub 0 plus c sub 1 times the quantity of x minus a plus c sub 2 times the quantity of x minus a to the power of 2 plus c sub 3 times the quantity of x minus a to the power of 3, and so forth. Since a power series involves a variable x, the series may converge for a certain value of x and diverge for other value of x. For a power series centered at x is equal to a, the value of a series x is equal to a is given by c sub 0. Therefore, a power series converges at its center. Some power series converge only at that value of x. Most power series, however, converge for more than one value of x. In that case, the power series either converges for all real numbers x or converges for all x in finite interval. In general, there are three possibilities or properties that can describe a power series in this form, depending on the precise series. One possibility is that a series converges when x is equal to a. Second possibility is that series converges for any value of x. Third possibility is that there are some positive number of r such that if the absolute value of x minus a less than r, the series will converge. And if the absolute value of x minus a is greater than r, the series will diverge. In this third possibility, this r is called as radius of convergence for that power series. These first two possibilities have also involved radius of convergence. It is simply that in the first possibility, the radius of convergence is 0, as there's only one value that will allow for convergence. And for the second possibility, the radius of convergence is infinite, as any value will allow for convergence. For a series c sub n times the quantity of x minus a to the power of n from n is equal to 0 to infinity, graph A shows a radius of convergence at r is equal to 0. This graph B shows a radius of convergence at r is equal to infinity. And this graph C shows a radius of convergence at r. For graph C, we note that the series may or may not converge at the endpoints x is equal to a plus r and x is equal to a minus.
For now, we will determine if the given example is convergent or divergent.
Let's try this first example. Take something the quantity of x minus 3 raised to the nth power over n. from n is equal to 1 to infinity. Remember in the ratio test, we change n to n plus 1. So this will become the quantity of x minus 3 raised to the n plus 1 over n plus 1. And we multiply this by the reciprocal of this original series. The reciprocal is n over the quantity of x minus 3 times n. To simplify x minus 3 to the power of n plus 1, we can rewrite that as x minus 3 to the power of n times x minus 3 over n plus 1 times n x minus 3 to the power of n. We can cancel out x minus 3 to the power of n, leaving us with x minus 3 times n over n plus 1. Now let's divide this fraction with n to get 1 over 1 plus 1 over n. As this is all positive, we can pull them out the absolute value brackets, leaving just x minus 3 in there. Now bringing n up to infinity, this whole part just becomes 1, leaving just the absolute value of x minus 3. In order to be convergent, this x minus 3, or the absolute value of x minus 3, must be less than 1. So given the absolute value, we know that x minus 3 must be greater than negative 1, but less than positive 1. Adding throughout positive 3 in negative 1, negative 3, and positive 1, we can get x between 2 and 4. So those values between 2 and 4 are the values that make the series converge. Let's answer the second example. X to the nth power over the square root of n from n is equal to 1 to infinity. We will use again the ratio test. When the limit goes to infinity, so everywhere there is n, we replace that with n plus 1. So this will become this x to the n plus 1 over the square root of n plus 1. And we will multiply this with the reciprocal of this original series. So the square root of n over x to the nth power. We will figure out again where this ratio is smaller than 1. But first, we will simplify. If the limit will goes to infinity, I have x to the power of n plus 1 here at the top and only x to the power of n at the bottom. So we can cancel out x to the power of n, leaving us with x. Because we can rewrite this x to the power of n plus 1 as x to the power of n times x over the square root of n plus 1 times the square root of n over the square root over x to the power of n. Cancel out x to the power of n, leaving us with x. And we can write this square root of n over square root of n plus 1 as one big fraction, all underneath the square root. So, the square root of n over n plus 1. Notice this our limit here all depends on n. So what does this mean is I can simply factor out the x. Simply factor out the x. comes out the absolute value of x, and we have that limit that goes to infinity of square root of n over n plus 1. But underneath the radical, if you think about the limit it goes to infinity of n over n plus 1, this is simply equals to 1. And what left is the absolute value of x. And we will going to figure out when that's smaller than 1. So, well, equivalently, this will give us an equation that x should be between negative 1 and positive 1. What we have at this point is, if we take any number between negative 1 and positive 1 and plug in this x, the series will converge. Third example, take x to the nth power over n factorial from n is equal to 0 to infinity. Let's also use the ratio test in this. We get x the power of n plus 1 over n plus 1 factorial. And we will multiply these by the reciprocal of this. So, n factorial over x to the power of n. Then we simplify this. Let's change x to the power of n plus 1 as x to the power of n times x. And let's change also n plus 1 factorial into n plus 1 times n factorial. And copy this one. Most of these cancels out. X to the power of n factorial. And we are left with x over n plus 1. Finding the limit as n approaches to infinity, we see that we will get 0 no matter what the value of x. To infinity, we get, if we change this n with infinity, we can get also n. So this means that the radius of convergence is infinity. The radius of convergence is infinity, and the interval of the convergence is from negative infinity to positive infinity. This is also fits on the second property or possibility that I mentioned earlier, which tells us that this series always convergent. Last example. Suppose we have a series n is equal to 0 to infinity n cubed times the quantity of x minus 5 to the nth power. So we will use again the exact same thing, which is the ratio test. When the limit goes to infinity, everywhere there's n, we replace that with n plus 1. It will become n plus 1 cubed times x minus 5 to the power of n plus 1. Since this is not a fraction, we will not multiply it by its reciprocal, but simply divide this by the original term. The original term is n cubed times x minus 5 to the power of n. Again, we need to simplify this one. We have a limit that goes to infinity. We have n plus 1 here in the numerator and only n of those in the denominator. So we will just left with x minus 5.
in the numerator, and I have n plus 1 to the third over n cubed. So we will write that as 1 as n plus 1 over n, all raised with 3. So same thing before, when the limit will goes to infinity, we can pull out this 5 from as absolute value of x minus 5. And we have left with the limit when it goes to infinity of n plus 1 over n, all raised to the third power. This n plus 1 over n, all raised to the third power, just equal to 1. So, in order to be convergent, we just left with x minus 5. So, in order to be convergent, this must be less than 1. So, given the absolute value, we know that x minus 5 must be less than negative 1, must be greater than negative 1, but less than positive 1. So, adding positive 5 throughout, we can get x is equal to or between 4 and 6. So, those values between 4 and 6 can make the series converged.